All right, so the plan for today is to start chapter 8 on applications and probability, starting with 8.1 arc length. Remember that the unit 1 exam is this week. I've mentioned several times about the exam, so I don't think this should be a surprise or anything, but just one last reminder: don't wait until the last minute to take the exam. Um, the exam is due this coming Sunday. But if you wait until the last minute to take it and there's some kind of tech issue or something, there are no extensions on the exam because it's open for a full week. You have a ton of time to take it, to schedule it. If you schedule it for, say, Thursday or something, and if something goes wrong, you have, several days to get that remedied. Work with me, work with, WebAssign or whatever you need to get things up and running. Don't wait until, Sunday afternoon, Sunday night or something to take the exam. So the Examity Practice exam is also up. So if you haven't taken the exam yet, and you also haven't taken the Examity Practice exam yet, take the Examity Practice exam first, just to go through all of the stuff with creating the Examity account and all those kind of things before the actual exam, just to make the actual exam process run a little more smoothly. And then the quote of the day really quickly is from a coworker that my wife worked with in St. Louis when she was working out there for a year. She liked to say that velocity is a vector quantity, so consists of both speed and direction. And so in other words, if you're trying to get something done, you need to point yourself in the right direction. If you have just a lot of speed, you might be kind of just running in circles. But also, if you spend a ton of time pointing yourself in exactly the right direction, you might never actually get moving. Or kind of my interpretation of this is something like effectiveness equals efficiency times effort. One of the traps that I kind of fall into is hyper focusing on efficiency. So if I want to learn something, maybe I'll try to research and find what are the absolute best sources, what are the best books or the best videos or something to learn this topic. And I spend all of my time and energy finding the most efficient way to learn it, but I never actually get off the ground and start putting in the effort and actually start learning. It would be better to have a slightly less efficient method, but put in the effort. So that's kind of my whatever vice or whatever is that I hyper focus on efficiency. But I think others, particularly the kind of Energizer Bunny folks who have tons of energy and just want to get started. That's not me, but there are a lot of people who are like that, and that's I admire those people that have that much energy. But if you just jump in and you have no idea what direction you're headed, you might spend a lot of time and energy spinning your wheels because you haven't, set out a strategy. I think this also applies to solving math problems, that if you're come up on a problem and you sorry, I'm still feeling a little bit under the weather today. Either allergies or still feeling under the weather, one of the two. But if you so I think the good approach is to be aware of the strategy of where you want to go, but also start taking steps in that direction. So if you read through a math problem or a word problem or something, and you might say, I'm a little bit stuck, I don't see the entire strategy of how to solve the problem. Ask yourself, can you take one step? Maybe you don't see the entire strategy, the entire direction, but can you take maybe one step? If it's a step in the right direction, maybe it leads you to the next and the next step, and then you get to where you're going. Or it might be a step in the wrong direction, but even that step in the wrong direction might give you some insight about the problem. And then in terms of career and getting a job or advancing in your career, I think the other thing to consider is relevance. One of the buzzwords today is you want to have an outsized impact on your institution, right? You want to be impactful to your institution, which means that you're effective, that you can do things, but also that the things that you can do are relevant to your institution. So if you're really good at doing something your institution doesn't care too much about, or that your boss doesn't care too much about, that's maybe going to have less of an impact. Not necessarily saying you shouldn't do those things, but just realizing that, what kind of impact that's going to have. Okay, so let's jump into arc length then. So this is the basic idea of arc length. Is suppose we have a curve f of x from A to B. And what if I kind of imagined a person kind of standing on this on a hill that, say, this curve represents a cross section of, and this person wants to walk from AF of A to BF of B, but they want to walk along the curve. And I wanted to ask the question, what's the distance or what's the length of the curve measured along the curve? What's the distance they would have to walk? We might be like tempted to just say, oh, B minus A, like if there was a flat surface, but clearly if, we could imagine that, if we had to traverse some kind of crazy thing like this, I think pretty clearly we can see that we're going to have to walk a much longer way than B minus A. So how can we find the length of a curve measured along the curve? Well, maybe one thing that we could do is our seemingly standard now Calc 2 trick. We have a continuous problem. If we break it up into a bunch of really small continuous problems, maybe on each of those little tiny subintervals, we can approximate the continuous problem with a discrete problem, solve the discrete problem on each of the little subintervals, take a limit, which will bring us back to an integral, and then we're back into the continuous world and we have the solution to the continuous problem, but kind of having passed through the discrete problem perspective. I just realized that I lost a side to my triangle over here when I copied this. There we go. Okay, so what I could do is I could zoom in on one section of my function. And one thing with nice continuous functions is when I zoom in on them, and particularly continuous and differentiable functions in particular, when I zoom in on them, as I see over here, I do have a curve, but that curve is pretty close to a straight line, right? I mean, we know from Calc 1 that locally, for differentiable functions, the tangent line makes a good approximation to the function. If I consider that I have a horizontal distance, delta x, that I traverse from the left to the right side of this little subinterval, this little chunk of the function that I've cut out, I then have a vertical distance, delta y. I have an arc length, I'll call maybe script L, of the curve. So this would be how far my little dude over here would have to walk along the curve. But I see that there's also a straight line length from this top left point to this bottom right point. We'll call that just capital L. And I notice that when delta x is small, script L, the arc length, is approximately just capital L, that straight line distance. I can't say this from A to B because there's lots of curviness and all of that happening from A to B, but if I pick a small enough delta x, this is approximately true, and the smaller that I pick delta x, the more true this is, the better the approximation is. But I also note that by Pythagorean theorem, I have a right triangle here going from horizontal to vertical at a right angle, and then a straight line connecting those, a right triangle, L squared is delta y squared plus delta x squared, or L equals root delta y squared plus delta x squared. Don't be careless with your arithmetic here or algebra here. This is not delta y plus delta x, but I can't actually factor out a factor of delta x squared. That delta x squared comes through the root as a delta x. So I can see my little component of arc length is approximately this for a small delta x. Now I could imagine, say indexing this. I could give each of these an I. I could then sum over a bunch of these little subintervals. So sum over I. And then I could take the limit as my delta x's go to 0. And what do I end up with? Well, delta y over delta x becomes dy dx, just the derivative, squared, plus 1. So this radical we see mirrored there. My delta xi becomes my dx. And I'm just integrating from a to b instead of summing. Right, so I've done my kind of standard strategy where, well, didn't realize it was going to jump around like that, but I've done my standard strategy where I take a complex continuous problem, zoom in, approximate with, in the zoomed in version, approximate with a discrete approximation, get a discrete approximation across the whole problem, and then limit to recover an integral. The integral which will be the exact solution to the continuous problem. Okay, so let's look at this example. Find the circumference of a circle with radius r. So here I have a circle, radius r. And I want to find the circumference. In other words, I want to find the arc length all the way around. Well, I'd really like to not have to deal with an implicit function. So I think what I'm going to do instead is just consider the top half of the circle and double the answer to get the circumference. I could even go a step further and just consider the first quadrant of the circle. So find the arc length, and then the circumference is 4 times that arc length. So I'm leveraging the symmetry of the circle here to let me just find the arc length in the first quadrant. This is going to be easier to work with. And then I just quadruple that to get my circumference. I see clearly these arc lengths in the other quadrants are all going to be the same. Okay, so what's my function then? I have y equals root r squared minus x squared for x in 0 to r. Now, something that you might be a little worried about is, let me see if I could move this down one line. There we go. So it's a little less scrunched than that previous line. Something you might naturally be worried about is we just finished up this chapter 7 where we talked a lot about integration techniques. We saw other integration techniques in chapter 5. We know that integrals, even of seemingly pretty simple integrands, can be pretty difficult to do, right? What do I have to do to my function? I have to differentiate it. I have to square it. I have to add 1 and then square root it to get my integrand. That's a lot of, like, in some sense, like unrelated operations. I'm a little worried, right, that finding arc length for, say, an arbitrary function, if I just give you a function, say, find the arc length, that might be a pretty tough problem because the integral just might be difficult to compute by hand. And that is a fair point. I think, again, talking a little bit about strategy and so on in solving these kinds of problems. When you get to things like Calc 2 and Calc 3, there's a lot more effort put into the problem statements to come up with problems that are reasonably solvable by hand within a reasonable amount of time. Right. So if I just gave you kind of an arbitrary function on an arbitrary interval and said, find the arc length, is it going to be possible in theory? Probably yes, most of the time. But is it practical to do by hand? Probably not. Even if it is possible to do by hand, it's, pedagogically, I don't really, if we're in the arc length section, I don't want you spending, an hour doing the integral and spending 3 minutes setting it up, right? Spending 3 minutes learning the arc length stuff and spending an hour doing what at this point essentially amounts to busy work. That's just not beneficial. So there is, the problems are somewhat cherry picked. They often have a lot of symmetry to them because symmetry often helps with simplifying the integrand, or with simplifying the interval, like we're doing here. We actually did both pieces here, made the integrand simpler, and we have an easier interval to work with. So this is one of the kind of strategic, practical things to look for symmetries, right? A lot of times the symmetries are baked into the problem intentionally to make the problem easier to do. But just, practically speaking, to be able to go through the problems and work through them by hand and actually learn the material, the problems are a little bit cherry picked. And if we had an arbitrary function that we wanted to compute the arc length of, if we got an integrand that wasn't, fairly easy to integrate, then we would just go back. We'd resort to, say, some approximate integration method. We'd either go to MATLAB or something and say, hey, integrate this function for me on this interval and give me a number out. Or we would, maybe write code ourselves or use code that somebody else has written or something like that. Okay, but with that out of the way, we have this problem. A lot of symmetry. We've really leveraged that symmetry to get it down to something a bit simpler. And I see that my arc length for this quarter circumference, well, it's going to be the integral from 0 to r. Well, I have this whole square root of stuff here. Let me actually come off to the side here and figure out what that's going to be. I don't want to have to write all my integral stuff 5 or 6 times. Okay, so if this is y, what is dy dx? It's going to be 1 over 2 root stuff. times the derivative of the stuff inside, which would be negative 2x. The 2's cancel. And I get negative x over root r squared minus x squared. dy dx squared is this stuff squared. Or, I gotta talk to my HVAC guy really quick. Be right back. Sorry. Sorry about that. They were just telling me they're finished up and they have to order parts. So, all right. So the dy dx squared is x squared over r squared minus x squared. 1 plus that. Well, that's 1 plus this fraction, which is r squared minus x squared plus x squared over r squared minus x squared. These go away. And then I want to square root that. So what does that give me? So that gives me r over square root of r squared minus x squared. And dx. Okay, so I want to do this integral. And I look at this and I say, okay, thinking back to chapter 7, I mean, I don't see anything right away that seems like a good candidate here, but maybe a trig substitution will work. What about x equals r sine theta? I have to be super careful with trig substitutions. I'm going to right away say what my dx is. R cos theta d theta. So I have integral of r over, and I suppose I will come off to the side for this as well. What is root r squared minus x squared? That is root r squared minus r squared sine squared theta, or this is r times 1 minus sine squared theta is cos squared theta, r cos theta. So this denominator is r cos theta. So I've brought down my r, I've brought down my denominator in the integrand. My dx is r cos theta d theta. So these cancel. Again, you can kind of tell that this problem is working out very nicely, right? And then lastly, when x equals 0, that's when theta equals 0. When x equals r, that's when sine theta equals 1. That's when theta equals pi over 2. So we're integrating from theta equals 0 to pi over 2. This gives me, well, just integral of r d theta is just r theta from 0 to pi over 2 is r times pi over 2. And remember, this is this intermediate step. This is the quarter circumference. And that's, of course, the circumference that formula that we all know. So circumference in this case is 2 pi r. Any questions on this one? Okay. Let me copy the formula. So next example, find the length of this curve, y equals log of cos of x, on the interval x in 0 to pi over 4. Okay, so I have y. What is dy dx? Again, I'll come over here and try to work out what my integrand is off to the side, just so I don't have to rewrite the integral and dx and all of that a whole bunch of times. The derivative of log of stuff is 1 over stuff times the derivative of stuff. So dy dx is negative sine x over cos x, or negative tan x. Dy dx squared is this squared, or just positive tan squared x. And then 1 plus dy dx squared is 1 plus tan squared x. But I know that like tan squared x is sine squared over cos squared. So I know that sine squared plus cos squared is 1. If I divide everything by a cos squared, I get a 1 plus tan squared equals 1 over cos squared, or secant squared. So 1 plus tan squared is secant squared x. And then, of course, I can square root this. So we get secant of x. So integral 0 to pi over 4 secant of x dx. And for this kind of an integral, in the supplement, I worked through the integral of secant of x. And it's not a trivial integral to do. We have to make it a 1 over cosine x. And then we have to make the 1 into like sine squared plus cosine squared. And right, that there was quite a bit that we had to do to figure out this integral. So for this one, I'm going to kind of cheat, and you could either, you could definitely pull up a table in your textbook, but let me bring up the window here, get my windows resituated. But we can just come over to Wolfram. We know that we've done this before, and it's some kind of big log and all of that kind of stuff. So we could look in the textbook, but in this kind of a situation, sometimes it works a little better too. And that's a bit of an annoying answer. So let's say from 0 to pi over 4. And we, get some kind of crazy answer, but we end up with approximately 0.8814. And again, we could, go with an answer like this, or, there are different ways that we could, um, that one of the downsides of something along these lines is that when you're dealing with logs and when you're dealing with trig functions is there's just 1,000 different ways to write the solution, right? So in this case, I'm just going to go with approximately 0.8814. We could plug our values from 0 and pi over 4 into here and see what we get out of this. We can simplify it, maybe get something a little bit nicer. Um, I think that personally, sometimes Wolfram Alpha tries to be a little bit too smart and give you something like this, and it's like what the heck is that? The inverse hyperbolic tangent of the tangent of stuff. That's because it has to do with logs, right? It's smart enough to figure out that it can write it as the inverse hyperbolic tangent. Um, so I think sometimes, in some sense, this is maybe a simpler answer in that it's exact and that it uses nice closed form expressions, but sometimes just having a numerical answer is maybe a little bit if not, I would say a little bit easier, but also a little bit more beneficial, right? I don't think there's much benefit to saying that we have twice the inverse hyperbolic tangent of some tangent of stuff. Then let's look at this curve. So here we have an implicitly defined curve, y minus 1 cubed equals x squared for x in 0 to 8. Okay, so what is this gonna what is this gonna look like? My right hand side is gonna go from 0 to 64. So then y minus 1 the thing that's getting cubed is going to go from 0 to 4 because 4 cubed is 64. Or y is in 0 to 5 when x goes between 0 and 8. So it looks like I have something like, maybe it looks something like this. I see I have something like y equals 1 plus x to the 2/3. So I guess maybe this starts around 1. But something like y equals 1 plus x to the 2/3, that has the feeling of something like 1 plus square root of x, maybe something like that. So maybe this is roughly what my picture looks like with x going from 0 to 8. So I can solve for y. 1 plus x to the 2/3. I know I need dy dx squared. Let's do dy dx first. The 1 plus differentiates off. The x to the 2/3 differentiates to x to the 2/3 x to the minus 1/3. Dy dx squared is 4 over 9 x to the minus 2/3, or this would be 4 over 9x to the 2/3. We have to do 1 plus this. So I could try to simplify something like this. If I'm looking ahead to square rooting, what am I going to end up getting out of here? Well, so I'm not sure that I'm going to end up with something that's super nice. I'm going to end up with, I suppose I could get a 1 over 3 x to the 1/3 out of here. But then that's going to be up against a square root of 9x to the 2/3 plus 4. Is that going to be a good result? Well, I do have x to the power 1/3 floating around there. Let me go down that route. Let's see if it works. So that's going to be what, 1 over 3 x to the 1/3 times the square root of 9 x to the 2/3 plus 4. And here I'm interested in, this is what my integrand could end up being. Do I see a path forward with this? Right? This looks pretty messy. I don't really see a path forward, say, at this point. But, I do recognize that I have different just power functions here. Can I make this work? Well, what if I maybe did a U substitution? U equals 9x to the 2/3 plus 4. What would du be then? Well, that's going to be 9 times 2/3. But if I differentiate this, I get x to the minus 1/3. This bit differentiates off dx. But nicely enough, I actually do see that it looks like this is going to work out okay. I just have some constants to fix, but I think this actually will be the right approach. So, back here, I didn't really have much faith that this was going to work. I didn't, again, kind of linking back to that, direction versus speed kind of thing. I wouldn't have really thought initially that this was likely to work out well, but I did recognize that, okay, I just have some power functions floating around. Let me take a couple of steps in this direction, see what happens. Maybe I get to this point and I say, that didn't really work. Let me rewind and consider a trig substitution or something. But in this case, it does seem like it's going to work. So I would need to integrate this whole thing, square root of 1 plus dy dx squared on 0 to 8. And this becomes that dx. So this is my du then. So I have integral, these bounds are in x. I have a square root u. So that takes care of this factor in the integrand. I have 1/3 x to the minus 1/3. They switch colors here. That takes care of these pieces with the dx. I have a factor of 18 in the du, so I need a 1/18 du to move those to the other side. So du with a 1/18 is the same as 1/3 x to the minus 1/3 dx. I've used everything in my integrand, nothing that's not in my integrand. I do now have to change my bounds. So when x equals 0, u is 0 plus 4, or just 4. When x is 8, so what is 8 to the 2/3? Well, that's the cube root of 8 squared. The cube root of 8 is 2, squared is 4. I have 9 times 4 plus 4. 10 times 4 is 40. So not the, prettiest lower and upper bounds, but that's what they are. This is u to the 1/2. So this integrates to u to the 3/2 times 2/3 from 4 to 40. Or what does this give me? The 2 and the 18 divide to give me a 9. So 1/27 times, what would this be? So 40, square root of 40. I don't think that's, there's a factor of 8 in there, but I think I'm just going to write it as 40 to the 3/2 minus 4 to the 3/2 isn't too bad. Square root of 4 cubed. Square root of 4 is 2. 2 cubed is 8. So I will simplify that one. We probably could, I guess we could take the 4 to the 3/2 and make that an 8, make it like an 8 over 27 times like 10 to the 3/2 minus 1. If we wanted to push it, maybe that's a little bit simpler, but I think this is about as nice as we're going to get. Any questions so far? And there's one last point that I want to make about arc length. And that's that arc length is the length of this curve. It's like this person walking along this curve. I could think of it as like a cross section of a hill. I could also just think of it as like if I just had a flat surface that the person's walking along, if they're just following a path on that flat surface. Does it matter a whole lot whether I index this with respect to x or with respect to y? Not really. It's the same length, right? It's not like if I was integrating, a function dy or something versus the x, that might maybe in some circumstances have a meaningful difference. But here, could I reinterpret my arc length formula in a different way? Could I also say that the arc length is integral from, let's say, c to d of square root of 1 plus dx dy squared dy? Or what did I really do? Well, if we come back up here to first principles to see why this isn't an unreasonable thing to do. Up here, I chose to factor out a delta x. Could I have gone a different route and factored out a delta y squared? Yeah, there's nothing wrong with just looking at the problem from a different perspective. Let me see if I can get all of this on one screen here. After I figure out what y goes from and to, so I think I do have to be careful here. I made a minor error here. Y minus 1 goes from 0 to 4. So y goes from 1 to 5. I think I drew it correctly on my picture over here, but just made a mistake in that lower bound of that interval there. So actually important to correct that first. But if I take this implicit function, can I solve it for x in terms of y? Integrate over y from y equals 1 to y equals 5. Yeah, sure, I should be able to do that. Now, if I solve for x in terms of y, I'm rapidly running out of space here. Let me just kind of plop this over here and then make a note. There we go. So I want to integrate y equals 1 to 5. And again, I want to integrate all of this stuff. So let me come off to the side. I need dx, dy. So I need to figure out what's x in terms of y. X equals y minus 1 to the 3 halves power. So what is dx dy? It is 3 halves y minus 1 to the 1 half times d dy of the inside, but that's just 1. Or this is 3 halves root y minus 1. What's dx dy squared? 9/4 times y minus 1. What's 1 plus dx dy squared? And it would work so nicely if that 9/4 wasn't there, wouldn't it? But it is going to be 1 minus 9/4 plus 9/4 y, or that's what? 9/4 y minus, so 1 minus 9/4 is going to be minus 5/4. And then if I square root this, so hard to write dx dy. It's just such a habit to write dy dx. I can see that this is going to be 9y minus 5 under the square root all over 2. I think pulling out that 2 is going to be helpful. So what is my integrand? It's 1/2 root 9y minus 5 dy. Okay, this gives me 1/2 integral. If I integrate square root of a linear, that's basically just like integrating square root of y, right? So this is linear to the 1/2 power. So I expect to get 9y minus 5 to the 3 halves times 2/3. If I were to differentiate this, the 3 halves times the 2/3 would cancel. I'd get stuff to the 1/2, which is what I want, but my chain rule would pop out a 9, so I need an extra 1/9 in front to fix that. Going from y equals 1 to 5. And this gives me, I guess these 2's go away. This gives me 1 over 27 times 9 times 5 is 45, minus 5 is 40 to the 3 halves, minus 9 minus 5 is 4 to the 3 halves. That's square root of 4 cubed. That's 2 cubed is 8. And fingers crossed is that the same thing we got down here, and it is. Somehow in amongst all of that arithmetic and algebra, I didn't make any mistakes. Or if I made mistakes, I made them exactly to cancel out or something. I don't know. But we do see that we could think of this in terms of X. We can think of it in terms of Y. Thinking of it in terms of X, we were able to use kind of our more basic formula, I suppose, or the formula we're more used to, but that resulted in an integral that was a little messier to do. Admittedly, it wasn't terrible. It wasn't, a 20-minute long integral, but if you gave me the choice between doing an integral with, where was it? An integral with this in the integrand, where I have a square root with an x to the 2/3 power inside, versus an integrand that's just the square with the linear inside, I'd much prefer the linear. So this is where sometimes taking a minute to strategize and say, well, do I want to give myself a 2/3 power, or would I rather give myself a 3/2 power? 3/2 powers, I mean, square roots, just especially when I know I'm going to be differentiating and then integrating, square roots just seem to work a little better, right? Because basically the derivative of a square root is 1 over the square root. So that's kind of a nice thing about square roots. The 2/3 power just seems a little more awkward to deal with. So even though I got the same answer in both cases, one answer was I had to do a substitution and be super careful with all my fractions and everything. And the other answer, I didn't have to do a substitution. I didn't have to change my bounds of integration. It was a pretty quick and easy integral to do. So that is a trade-off, right? If I have a function like this where I can imagine it as y as a function of x or x as a function of y, and from either perspective, that doesn't change the arc length, the length of this curve, but one way might be easier to actually work out the answer than another way. So always something to kind of keep in mind, But again, you can kind of over focus or hyper focus on what's the best strategy and spend 10 minutes figuring out what the best way is to set up the problem in order to avoid to change, say, a 2-minute integral into a 1-minute integral. Or you could just start, running with straight ahead without any plan, and you could end up running into a 20-minute integral. And if you never rethink things and say, is there a better way to approach this? That's probably not the best strategy either. So especially on problems like these, where, again, like I mentioned, in a lot of these Calc 2 problems and a lot of Calc 3 problems, the problems are kind of cherry picked to be reasonably doable. But sometimes if you take the wrong approach, they become really, really hard to do. So if you start down a path and it's like, wow, this is looking really messy, don't immediately assume that you did something wrong, but ask yourself, okay, if I rewind a couple of steps based on what I knew before and maybe what I learned from doing it this way, is there another insight I have? Is there a way that I can approach this problem slightly differently to make my life a little bit easier? Sometimes there is, and frankly, sometimes there's not. Sometimes you just have to do the annoying integral with the fractional powers. But sometimes there is an easier approach. Are there any questions on anything that we talked about today, on anything about arc length, or any questions about the Unit 1 exam?
Okay. I had a few questions about the exam, but it's personal, so it can wait until after we wrap.